So we've seen that the tools of linear algebra let us compute a lot of interesting things about linear transformations and about, these vectors that are arrows in Rn. But if we could figure out, a more general context in which we can use vectors, we could apply these tools that we have to lots of other situations. So what we should do is figure out what exactly is it about vectors in Rn that make all of linear algebra work. When you get right down to it, there are only a few things, or a few properties of vectors in Rn that actually are required to make linear algebra go. And these are what those properties are. So anything that satisfies these properties we'll call a vector space. So what we need is first a collection of things that we're going to call vectors. Now, as we discuss this huge list of properties, keep in mind Rn, right? Rn is really going to be our template for what a collection of vectors looks like. So any collection of vectors that satisfies this list, we're going to call a vector space. So Rn will turn out to be a vector space. Okay, so first we need a collection of vectors, and for Rn, it's just all of the vectors in Rn, right? All of the column vectors with n entries. So that's our collection of vectors. And also we'll need a choice of scalars. We will almost always use the real numbers for our scalars, but in general it could be the complex numbers, and in fact it could be anything that is sort of a universe of numbers where you can add, subtract, multiply, and divide. And in general, that type of mathematical object is called a field. That's not important, but that's what it's called. So for our scalars, we'll always use the real numbers. In addition to a collection of vectors, we have two vector operations. We have a way of adding vectors, and we have a way of multiplying vectors by scalars. Right? And that's true for Rn. To add vectors, we're just adding component-wise, and to do scalar multiplication, you just multiply by a scalar component-wise. Now, these vector operations have to satisfy certain properties to count as being proper vector operations. And this big list of properties is just all of the properties that we already know that vectors in Rn satisfy. So your vector addition has to be, or your vector space, so I actually haven't named my vector space, so vector space, let's call it V. Oh, here it is, I did name it. If you pick any two vectors out of your collection of vectors, when you add them together, you have to get another vector. So the term of art for this property is saying that your vector space has to be closed under addition. Also, it has to be closed under scalar multiplication. That's way down here. If you choose a scalar and a vector, when you multiply them with your scalar multiplication operation, you have to end up back in your vector space. Your addition has to be commutative, which vector addition in Rn definitely is. Your addition has to be associative, which vector addition in Rn definitely is. There has to be an additive identity, which we will call 0. What we mean by additive identity is just that when you add any vector to your additive identity, you get the same vector back, right? So this thing is acting like the 0 vector. And there definitely is an additive identity in Rn. It's the 0 vector, right? Like this. So this using 0 as our notation for the additive identity is very suggestive. Also, we have to have additive inverses. So for any vector, there has to be another vector called negative v, so that when you add them together, you get the 0 vector. All right, scalar multiplication has to satisfy a few properties, so we have to have closure under scalar multiplication. Scalar multiplication has to be associative, and when you multiply a vector by 1, you have to get the same vector back. Okay. Without this property, it would actually be possible that 1 times a vector gave you some other vector. So we have to explicitly say that multiplying by 1 gives you the same vector back. In addition to these properties for these operations, scalar multiplication and vector addition, individually, there are two rules that they have to follow together, and that is distribution. So scalar multiplication has to distribute over vector addition, and scalar addition also has to distribute over scalar multiplication. So all of these properties, we already know that all of these are true for Rn. So Rn is our first example of a vector space, right? There's not really, so Rn is a vector space. There's not really anything to prove here because when we first sort of described what vectors are and what these operations, vector addition and scalar multiplication are, we actually checked all of these properties. So there's nothing left to prove here, right? So Rn is a vector space. And in fact, when we think about vector spaces in general, usually we'll picture in our minds Rn, just because we're so familiar with it. But what we'll see is that there are other vector spaces besides Rn that will be of some interest.